Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss Clausius-Clapeyron and Ehrenfest equations. Let's begin. Clausius-Clapeyron latent heat equation. So, we have to know what is latent heat. The quantity of heat, let del Q, absorbed or given out by a substance during its change of state, which is directly proportional to the mass of the substance. Means del Q is directly proportional to the mass of the substance m, or to remove that proportional we use the proportionality constant. Del Q is equal to proportionality constant L into m. Here L is known as the constant which is known as the latent heat. Of that of substance, and it depends upon the nature of the substance. We have to define the latent heat. Now here we have to put, let m is equal to 1, then del Q is same as L, that latent heat which depends upon the nature of the substance. So, how we have to define the latent heat of that of substance? Now, we define thus the latent heat of a substance is defined as the amount of heat absorbed, or given out by a unit mass, m is 1, by a unit mass of the substance to change its state without the change of temperature. The change of temperature. In this way, we define the latent heat of that of substance, means the amount of heat absorbed, or given out by a unit mass of the substance to change the state without the change of temperature is known as latent heat. Now, Clausius and Clapeyron derive a equation related to this latent heat. How they derive? They proceed like this. From Maxwell's second thermodynamic relation, relations, that is del P by del T at constant volume is equal to del S del V at constant temperature. Here we have to substitute. We know that the entropy according to the second law of thermodynamics, dq is equal to Tds. Therefore, del S will be del Q by T. Putting this value here, we have that is del P by del T at constant volume is equal to 1 by T del Q by del V at constant temperature. Now, for a unit mass of the substance, the amount of heat absorbed or released is the latent heat of that of substance L, as we discussed here. That is, here for unit mass, therefore, del Q is equal to L for unit mass. So, that equation changes to del P by del T at constant volume is equal to L divided by T del V, where del V is the V final minus V initial, the change in volume. That is the final volume, this is the initial volume, this is the final volume after the change of the state, Vi the initial volume. Per unit mass, Vf is the final volume per unit mass, Vi is the initial volume per unit mass. Let Vf is the final volume per unit mass, Vi is the initial volume per unit mass. Now, that equation written like this, del P del T at constant volume is equal to L divided by T Vf minus Vi. This equation, this is an important equation, and that equation is known as the Clausius-Clapeyron, that is the Clausius-Clapeyron latent heat equation, and this is the general relation which applies to change of state involving latent heat. So, this is Clausius-Clapeyron latent heat equation. This is the definition of latent heat. Then we use the thermodynamic relation here to derive an equation. That equation is known as Clausius-Clapeyron latent heat equation. We have to derive the Ehrenfest equation. How? It is necessary to introduce another equation, Ehrenfest equation. Due to some drawbacks in Clausius-Clapeyron equation, one of the limitations of the Clausius-Clapeyron equation is that the specific heat capacity and specific volume, do not change in the second order phase transitions. That is why we introduce Ehrenfest equation, that derive some equations by Ehrenfest which relate the changes in specific heat capacity and derivatives of specific volume in second order phase transitions. Here the drawbacks of Clausius-Clapeyron equations. To solve that drawbacks, the scientist Ehrenfest introduce new equation which solve the drawbacks, as which relate the changes in specific heat capacity and derivatives of specific volume in the second order phase transitions. This is the introduction to Ehrenfest equation. So let we have to derive what is exactly the Ehrenfest equation is. So right here, let us consider the specific entropy. Let us consider the specific entropy S, which is a function of temperature and pressure. Temperature and pressure, that is S is a function of temperature and pressure. Now differentiating, we get ds is equal to del S by del T at constant pressure. So it will be dt plus del S by del T at constant temperature, it will be dP. But we know that, T del S by del T at constant pressure is equal to Cp, which is known as specific heat at constant pressure, that is the specific heat at constant pressure, and del S by del P at constant temperature is equal to negative del V by del T at constant pressure, that is from Maxwell's equation, Maxwell's relation. So that equation becomes, therefore equation 1 becomes, putting the values here, we have the differential ds is equal to Cp by T dt minus del V by del T the constant pressure dP. For second order phase transitions, what happened? For second order phase transition, due to the continuity of specific entropy, the continuity of specific entropy the specific entropy S is constant, since the entropy is continuous, that is ds will be 0, change in entropy, that can be written like this: ds1 minus ds2 is equal to 0, where we consider 1 and 2 corresponds to 2 phases, 1 and 2 are 2 phases. So ds1, therefore for ds1 we write, that is C1 P by T dt minus del V1 by del T constant pressure dP. Next, for second phase, and for ds2 that is c 2p by t dt minus del V2 by del T and constant pressure dP. Let equation I and double I. So, what happened? Equating 1 and 2 means ds1 is equal to ds2. So, that equation, after equating, we write here equation I and double I, we get ds1 is same as ds2. So, that equation is same as that equation. So, write here c 1p t dt minus del V1 del T and constant pressure dP is equal to c 2p by t dt minus V2 del T and constant pressure dP. Now, here that is c 1p by t dt minus c 2p by t dt is equal to that to that side. So, del V1 by del T and constant pressure dP minus del V2 by del T and constant pressure dP, or del Cp by T dt is equal to del V by del T and constant pressure dP, or del Cp by T is equal to del V by del T constant pressure, that is dP by dt, dP by dt. That equation, that is the equation which is known as, that is the Ehrenfest first equation. This is Ehrenfest first equation. Here we take entropies as a function of temperature and pressure. But similarly, if we take entropy as a function of temperature and specific volume, similarly let us consider, let me consider specific entropy is the function of temperature and specific volume, Therefore, the equation looks like, that is del Cv by T is equal to minus del of del P by del T at constant volume dV by dt. That is the Ehrenfest second equation. This is the Ehrenfest second equation. Again, if we take specific entropy is a function of, if we take specific entropy is a function of volume and pressure, then that equation changes to, that is del V by del T at constant pressure is equal to del P by del T at constant volume dV by dP. This is the Ehrenfest third equation. Ehrenfest third equation. Now, again, if the specific entropy is a function of temperature and pressure, if that specific entropy is a function of temperature and pressure, then the equation looks like this: del V by del T at constant pressure, that is minus del V by del P at constant temperature del P by dt. This is the Ehrenfest fourth equation. Ehrenfest fourth equation. Look at these equations. This is the Ehrenfest first equation. This is the Ehrenfest second equation. These two equations are very important to calculate the second order phase transitions, but these are the next two are the accessory equations, that is Ehrenfest third equation, the Ehrenfest fourth equation, taking as entropy as a function of volume and pressure, entropy as a function of temperature and pressure. But first is cases, that is entropy is a function of temperature and specific volume. Here the temperature and specific, it we consider at constant pressure, the specific it at constant volume. So, with the help of this visual lecture, we understand what is Clausius-Clapeyron latent heat equation. This is the Clausius-Clapeyron latent heat equation, an Ehrenfest equation for the second order phase transitions. The Ehrenfest equation, entropy as a temperature and pressure, taking these relations, proceeding like this, and finally we take the equation which is the Ehrenfest first equation, taking entropy as a function of temperature and specific volume, and the Ehrenfest second equation. These two equations are important one. This one is very important to calculate the entropies or to calculate the second order phase transitions. Next, another two, entropies third equation and entropies, Ehrenfest third equation and Ehrenfest fourth equation. These are the Ehrenfest first equation and Ehrenfest second equation. So, with this useful and informative notes, let me wind up this session. Thank you.